So this is a great topic. Our closest star, the sun, and this is a beautiful image of the sun. We're going to, in our sun labs this semester, actually be able to kind of see some sunspots and maybe some of these prominences, but just a beautiful, beautiful thing. So we've talked about the reason that we see the planets like Venus right now in the morning sky. The reason we see Venus is not because Venus has any sort of mechanism in its core to create energy. We see Venus because the sun is shining on Venus, and that some of that light then is bouncing off to us. So we see the planet. So how does the sun get its energy? And actually, we already talked about how the sun gets its energy. We said it gets its energy through, I think we did anyway, through nuclear fusion in its core. But let's just say that the sun didn't have nuclear fusion in its core. Let's say that instead it was a regular combustion sort of chemical reaction, kind of like you burn wood here on Earth. Well, if that were the case, then the lifespan of the sun would be about 10,000 years. And you know how when you burn a log, a piece of wood, it has a limited amount of time it can burn, and so it's not on fire. Okay. Well, is the sun contracting? Is the sun still getting smaller and smaller? Because remember when we talked about the nebular theory, we said that contraction was important for that solar nebula to the majority of the material contracted in the center and formed our sun. Well, no, it's not contracting anymore, because the contraction would give us some heat and it will glow, and it did glow. But that's not the reason that it shines, because if that were the case, then this contraction would go ahead and give thermal energy to this star for about 25 million years, and then it would stop. I mean, you couldn't get any more energy from this contraction process per se. And as remember, we said that the meteorites that we pick up here on Earth, that the primordial meteorites are running about 4.6 billion years old. So meteorites are leftovers, kind of from when our sun first turned on 4.6 billion years ago. So it's not contraction. What is powering our sun, what's the reason our sun is shining with so much energy in all directions, is because in its core it is converting matter to energy. According to Einstein's, energy is equal to the mass of matter being converted times the speed of light squared. E is equal to mc squared. So we do have a nuclear reaction going on in the core of our sun, just like nuclear reactions are going on in the core of all living stars. So, and we're going to see in the next chapter, we're going to talk about stars and how they live their lives. And a star lives its life according to basically the amount of mass it started with. And so based upon the amount of mass that our sun started with, it should last from beginning to end of its main sequence about 10 billion years. So if we said that our space rocks are about 4.6 billion years, okay, so we have what, another 5.4 billion years to go, or as the sun is at 1. So we'll be talking more about that later, but this modeling of our sun converting, having nuclear fusion in its core, this is consistent with an age now of living 3, 2, 1. So there you go. Our sun must be powered by nuclear fusion in its core. And we'll talk more about that coming up. So one of the things that's important to understand the overall structure of our sun is that as you go from the outer edges of the sun towards the sun's core, we have greater and greater pressure. And I think we had a very similar figure to this when we talked about Jupiter the other day. But all planets and the sun also, as you go towards the core or the center of the object, pressure increases. And that's important for sustaining fusion in the core of our sun. So a little bit about our sun. We're going to actually later on compare other stars to our sun. Our sun is a very typical star. Its radius is about, you'd have to take 109 Earths, stack them side by side, and you would get the radius of the sun. The mass of the sun, you would have to take about 300,000 Earths and combine them all together. You would get the mass of the sun. And every star has what we call a given luminosity. And luminosity basically is the amount of energy that that star is pumping out per second. So the luminosity of our sun in terms of watts is a really big number. Remember, we oftentimes pack numbers up in scientific notation in astronomy. And so this would be, you take the 3.8, you take that decimal and you move it over to the right, 26 places. And that's how big, how many watts, how much energy this sun is pumping out per second in terms of watts. So let's just take a look at kind of the overall structure of our sun. The green arrows here are kind of showing you the force of gravity. And a few slides ago when I showed you the pillows, the top pillow being fluffy and the bottom pillow being squished, that's kind of what we have going on here. Notice that as you get closer to the sun's core, you get more and more squished. And gravity becomes stronger, actually, and material becomes denser. Okay, so pressure is greatest deep in the sun. And that little red spot in the middle, actually that's going to be our powerhouse. That's the sun's core. And only there are the conditions ripe or sufficient for fusion, nuclear fusion to occur. Well, once nuclear fusion occurs and you have the whole energy being created in the core, we have an outward pressure, and that's indicated here with red arrows. Okay, notice that the outward pressure is greatest near the core and it lessens as you go out. But that outward pressure is important. And if a star, such as our sun is, if that inward pull of gravity is exactly balanced by that outward pressure created by nuclear fusion, then the star is neither getting smaller nor is the star getting larger. And we say it's at equilibrium. It's at what I call its happy place. And that's the case with our star, the sun. And it'll be that way for another, 5.4 billion years. So we have this equilibrium situation. Gravitational equilibrium is one way to express it, that the pull of gravity towards the core is balanced by the push of radiation from the core produced by nuclear fusion. We also have this energy balance going on, which is kind of fun. So the sun is creating energy in its core, and that energy, and we'll talk more about this, but the energy kind of wiggles out, and it takes a long time for the energy to wiggle out. But when it gets to the sun's surface, it radiates away in all directions, creating what we call the luminosity. And the amount of energy radiating away is exactly balanced by the amount of energy being created. Isn't that cool? Our sun is its vital statistics are very stable. Okay. So just to kind of, I mentioned that red spot there in the middle, that core, actually only here are the conditions suitable for nuclear energy, for nuclear fusion. And what nuclear fusion needs is heat and pressure. And those two conditions exist and were created it took a while. You know, when we talk about the nebular theory, remember that we had a proto-sun before we had the sun. So the proto-sun was getting ready to become the sun, and the core needed to get sufficiently hot and dense before nuclear fusion could happen. So this again is kind of looking at the sun again. In the middle we have the core, and now I've added sort of, can you see some multiple layers? Let's kind of look at some of those layers. Before we look at the internal layers though, let's look at what's happening outside of the sun itself. We've talked a lot about solar wind, and now maybe you can kind of envision that solar wind actually being a product of the nuclear fusion that's happening in the sun's core. All stars have solar wind, by the way. Or excuse me, all stars would have what we call stellar wind. Our sun has solar wind. So the outermost layer of the sun's what we call atmosphere is the corona. And actually, it's kind of strange because it is the hottest most layer. Its temperature is about 1 million Kelvin. So it's weird that it's so hot out there and then it gets cooler as you go onto the next layer of the atmosphere. So closer to the sun in the corona, we have the chromosphere, which is a little bit cooler. And then we have the photosphere. And the photosphere has been kind of described as that's, if you glance, now never look at the sun, all right? You don't get lab credit for looking at the sun. It does not take much for you to ruin your eyes. But if you glance up at the sun, the photosphere is the layer of the sun that you're actually looking at. And I don't know if you remember, but we did these radiation curves where you could kind of estimate the surface temperature of a star based upon the profile of the radiation it was sending us. We call these radiation curves. And we figure the surface of our sun is about 5,800 Kelvin. And so that's what we're gauging it from, is the photosphere. And then we kind of get into the nitty-gritty of the sun. So here we have, you might recognize these. Remember we said that the Earth has convection cells that actually are kind of moving our plates on to make our plate tectonic movement of the Earth's crust. Well, kind of along those lines, there is what we call this convection zone of kind of, it's not really liquid. Is it liquid or plasma? Maybe it is liquid. But we have these little convection zones here just underneath the photosphere where warm material is rising and cooler material is sinking. Okay, can you kind of see these convection cells? And what they do is they help transport heat outward, from the core outward. So these would be just underneath the photosphere. And then underneath the convection zone, we have the radiation zone. And the radiation zone is a way of getting thermal energy from the core outward. And the radiation zone is what I call kind of butt to butt to butt. It's the energy is being transferred from by bumping. Okay, instead of convection, it's more like conduction in the radiation zone. And then in the center there we have the core, and the core is hotter than the corona. The core is where our fusion, our nuclear fusion, is occurring. And remember, in order for fusion to occur, we need to have immense temperature and immense pressure. That only happens in the core of a star, or if it's going to happen associated with a star, it's going to be in the star's core.